Hello everyone, I'm Ditlev Hartmann Bornebusch. I'm a master's student studying life science engineering and informatics. I'll be presenting recent work from the Center of Fundamental Living Technology at the University of Southern Denmark. That is, reaction kinetics exploration of a protocellular metabolism. I worked on this together with Hans-Joachim Ziock and Steen Rasmussen. A special thanks to Mike Ditlev, Sarah Mara, and Jim Bonzella. Now let's begin. In earlier work involving several of the authors of the current abstract, an attempt was made to develop an extremely simple protocellular organism that involves self-assembly of its components due to their association properties. In general, any living system has three elements required for its continued existence and its progeny. The elements are a metabolism, an information component, and a container that enables the two previous components to be in close proximity and helps to control their local internal environment. These three components need to exist in an exterior environment that both supplies the organism with resources and acts as a sink for its waste products. In our case, the information and metabolic components are fused together, and so the reaction between the two is simplified. The relevant components have been colored to make it easier to digest a reaction diagram that I will show you next. The free energy delivered to the system is in the form of light, and the resource components consist of a building block for the container and a hydrogen source. Now let us take a look at the reaction kinetics. In the upper right hand corner we have the previous figure for your reference. We have highlighted species with colored circles according to the role in the protocell system. For example, the green circles are container species. Note that the circles with both blue and red symbolizes the fused information and metabolic components. The protocell involved consists of decanoic acid that, under the correct pH and concentration conditions, self-assembles into bilayer vesicular container structures. The metabolism involves a ruthenium tris bipyridine-based photocenter that upon excitation undergoes an internal electron transfer via a metal to ligand charge transfer process. If the transfer is not stabilized, it will return to the original configuration and emit fluorescent light. However, the transfer can stabilize by having an electron donated from a modified nucleobase, 8-oxoguanine, that is covalently bonded to the ruthenium-based photocenter. The stabilized photoexcited compound can donate the electron back to oxoguanine, so R3 also has a path to the original configuration. Now, if the stabilized photoexcited compound lives long enough to donate the photoexcited electron to an oil-like precursor molecule, a picolinum ester, the precursor then undergoes cleavage, generating a decanoic acid and a waste product picolyl group. We have modeled the chemical system using the law of mass action to define differential equations for the rate of change of reactions. We describe the change in concentration of the excited ruthenium complex R2 with three terms containing a product of the rate constant and the concentration of R2. The positive forward term contributes to the formation of R2, and the two negative reverse terms reduce the amount of R2. Here on the left hand side we have all rates for the species from the reaction kinetic scheme described by differential equations. On the right we have a table of rate constants and their estimated values. Now let's take a look at how we determine some of the reaction constants. The hydrolysis rate can be derived from this differential equation if we have the experimental values for the hydrolysis waste product, POH. However, an experiment with guanine covalently bound to the ruthenium complex instead of oxoguanine yields the same as a photocatalytic experiment with no light. Thus, only hydrolysis drives the lipid reduction. In that case, the concentration of POH becomes equivalent to the total lipid concentration. We determined the hydrolysis rate to be 4.5 times 10 to the minus 6th per second. Here we determine the photoexcitation rate constant and the quantum yield. On the left we have a plot of the total lipid production for the experiment with the light activated photocatalyst, from which we found the lipid turnover rate. We determined the photoexcitation rate constant from the excitation rate, and the excitation rate is photons transmitted and absorbed per square centimeter second. This value is calculated from the areal power density of the laser, the amount of light absorbed by the sample, and the energy of a 405 nanometer photon. And we divide this areal density of photons absorbed per second with the areal density of catalyst molecules, and find that per second each catalyst molecule absorbs 0.48 laser photons. And we have to note here that it's not all photons that result in a photoexcited ruthenium. And now we move on to calculating the quantum yield. And by dividing the turnover rate, which is the amount of fatty acid molecules that are produced per second, with the number of laser photons each catalyst molecule absorbs per second, we get the quantum yield to be 0.44%. Here we have all the reaction states for a photocatalytic simulation over the course of 24 hours expressed in molar concentrations. Over here we have the reaction constants listed, and we have the initial concentrations for all species listed. We have to notice here that the combined lipid graph, we greatly overshoot the experimental data plotted in gray. We see that it fits nicely in the beginning, and then something happens. We believe this difference is caused by aggregates. Here we have the same figure blown up, but with the addition of the non-photocatalytic simulation colored in orange, where only hydrolysis of the precursor produces lipid. And here we also see a divergence of simulation data from the experimental data, as we see for the photocatalytic simulation. To get a better understanding of the formation of aggregates, we have three epifluorescent micrographs showing the aggregate formation at different times for both the oxoguanine and guanine experiment, that is with and without photocatalysis. The micrograph in the left bottom corner depicts a sonicated solution of small precursor drops before light is applied to the sample. Note that the drops are so small that they cannot be seen on the micrograph. They are around 10 nanometer in radius. In the right bottom corner, we have a micrograph of the guanine-linked photocatalyst experiment showing a giant vesicle in the late stage of the experiment. In the top right corner, we have a micrograph of the oxoguanine-linked photocatalyst experiment showing vesicles and other membranous structures. With rate constant corrections shown in inset A and B that are based on our understanding of aggregates, we were able to obtain a decent fit to the experimental data. These solid lines are simulations that includes the rate constant corrections, and for inset A we corrected the hydrolysis rate, and for inset B we corrected the electron transfer to precursor rate, which is KBE2. Let's take a deeper look at these linear functions that allowed us to approximate the aggregate effects. Inset A shows the simplest hydrolysis rate dependency we found. This time dependency is likely caused by the many small precursor droplets that aggregate slowly. It starts with sonicated precursor droplets that are about 10 nanometer in radius, and it ends with vesicles that are about 1 micrometer in radius. Starting from the end and assuming that the volume is constant, we have an expression for the total droplet area as we split one droplet into n droplets. From this we have the one droplet split into n equally sized smaller droplets increases the area with a factor of n to 1/3. Using the change in droplet radius, we estimate that the area is reduced with a factor of 4.6. Let's take a look at inset B. The rate for the electron donation to the lipid precursor, that is KBE2, is dependent on the total lipid concentration. First, fatty acids associate with the precursor droplets, forming a monolayer. Here KBE2 is constant until the critical vesicular concentration is reached and membrane structures start to form. The membrane formation creates a new area for the ruthenium complex to attach, and so the membrane quote-unquote dilutes the precursor from the photocatalyst, which decreases KBE2 depending on the lipid concentration level. At some point the precursor concentration becomes so low that it is quote-unquote dissolved inside the membrane, which causes the last flat area for KBE2. Now that we have done this analysis and we roughly understand the reaction kinetics, we can say that this protocell model is sufficiently good at producing membrane material. Future work includes the separation of the information component from the metabolism. That is, the oxoguanine should not be covalently bound to the ruthenium complex. Sarah Mora and others have already showed that this is possible. On top of that, an additional lipophilic tail is needed for the molecules to better associate with the membrane, which has been shown to improve the reaction kinetics of such a system. As an aside, we note that the same chemistry as we have used here is compatible with a DNA ligation mechanism demonstrated by Cape and others, which allows for photo-driven DNA replication. To conclude, we have made a detailed simulation of the Flint protocell info metabolism. We show how the Flint protocell metabolism works and how it interacts with the information component. Thank you all for listening. This has been a pre-recorded talk because I have experienced quite a lot of power cuts lately, so I might not be able to attend the Q&A session, but you can always find me on Slack. Thank you.